Somewhere up there, about 13 billion miles away, two NASA spacecraft are racing through the solar system.
6 years ago, NASA's Voyager probe made history by becoming only the second piece of artificial spacecraft to formally leave the solar system and travel beyond it. The second Voyager spacecraft, named Voyager 2, was launched on August 20th, 1977, 16 days before its identical twin, Voyager 1, left the solar system through the northern hemisphere. Voyager 2 is the only spacecraft ever to have made close flybys of Uranus and Neptune because it was launched on a more extended mission. After that, it headed into the heliosphere's southern hemisphere. Now, billions of miles from home in the blackness of space, NASA's Voyager has marked a milestone of exploration and is shedding light on some of the biggest mysteries of our solar system. What unnatural phenomena has the Voyager discovered? Let's find out. On August 20th, 1977, the Voyager 2 spacecraft of NASA launched on a Titan III Centaur rocket from Cape Canaveral, Florida, beginning a grand tour of the solar system that would see it travel to the Jupiter and Saturn systems, as well as become the first spacecraft to travel to the ice giants Uranus and Neptune and their moons. The Voyager mission, which consisted of two probes, was created to take advantage of a once every 176-year alignment in the 1970s that allowed for gravity-assist slingshots between planets throughout the solar system. The first to launch was Voyager 2, with Voyager 1 following 2 weeks later. Both had the renowned Golden Record, a 12-inch copper disc that had been gold-plated and contained sounds and visuals that showed the variety of life and culture on Earth. Voyager 1 is currently the farthest artificial object from Earth, located around 14.5 billion miles away. However, Voyager 2 is likely more recognizable due to its amazing multi-decade journey through the massive planets. Even though it was the second spacecraft to launch, Voyager 1 was given that name because it was intended to arrive at Jupiter and Saturn first, in March 1979 and November 1980 respectively, before leaving the planet's orbits and taking the iconic pale blue dot picture. Jupiter in July 1979, Saturn in August 1981, Uranus in January 1986, and Neptune in August 1989 were the four planets that Voyager 2 visited. Both Voyager 1 and Voyager 2 left behind significant contributions to planetary exploration, not only in terms of the scientific work they achieved, but also in showing that it was actually possible to explore the outer solar system with a few spacecraft. What was discovered by the Voyager probes? For many planetary scientists who still rely on the exceptional photographs from the spacecraft's wide-angle and narrow-angle sensors, Voyager's discoveries are the stuff of folklore. The probes determined that Jupiter's Great Red Spot is an Earth-sized storm, that the gas giant has weak rings, and that the moon Io of Jupiter has volcanoes. They investigated Saturn's rings, observed the thick Earth-like atmosphere of Titan, the huge moon, and discovered that Enceladus, a small moon, was geologically active. Then, Voyager 2 by itself traveled to Uranus and Neptune. The first ever photographs taken by the spacecraft of Uranus showed its black rings, skewed magnetic field, and its geologically active moon, Miranda. While this was happening, it was also found that Neptune had much more moons and rings than previously imagined. We also got to observe Triton, which, like Pluto, is now thought to be a captured dwarf planet from the Kuiper Belt. Triton is a geologically active moon that orbits backward. Voyager continued to provide new information on the mysterious outer planets, and the fearless probes carried on. By the early 2000s, it appeared likely that one or both would cross the heliopause when the solar wind, the sun's explosion of charged particles, peters out. The heliopause is the border between the heliosphere and interstellar space. The fact that the probes were designed primarily to investigate Jupiter's massive magnetosphere rather than the much weaker fields and particles of the interstellar medium dampened that exciting potential. When Voyager 2 passed through the termination shock in 2007, which is where the solar wind first begins to waver as it is buffeted by the interstellar gas and dust the solar system is speeding through, it was a great surprise. Voyager 2 was sinking below the ecliptic plane in which the planets circle. 3 years prior, Voyager 1, which was 94 astronomical units (AU) from Earth, had traversed the shock. around 150 million kilometers separate Earth and the Sun on average, or 1 astronomical unit. However, because its plasma detector at Saturn had malfunctioned in 1980, it was unable to measure the solar wind's slowdown. The wind was expected to slow down from 1.2 million kilometers per hour to roughly 300,000 kilometers per hour in accordance with models. However, Voyager 2 measured a wind speed of 540,000 kilometers per hour. The fact that Voyager 2 crossed the Shock 10 astronomical units closer to Earth than Voyager 1 was also puzzling. The characteristics that characterize the solar system's periphery, such as the composition of solar winds, the behavior of plasma particles, the interaction of cosmic rays, the direction and structure of magnetic fields, and others, may all be studied by the spacecraft. Voyager 1 did defy expectations, but its insights were hardly all-encompassing. Its plasma temperature measurement device stopped working back in 1980. However, Voyager 2's plasma instrument was still in excellent condition, allowing for a considerably clearer view of the heliopause when it passed on November 5, 2018. For the first time, scientists could observe that the plasma surrounding an object slows down, warms up, and becomes denser as it approaches the heliopause by 140 million miles. The interstellar medium is at least 54,000 degrees Fahrenheit on the opposite side of the boundary, which is hotter than anticipated. The average temperature in the area surrounding the Voyager probes, however, continues to be quite low since this plasma is so thin and diffuse. The heliopause is also a leaking barrier, and the leaks flow both ways, according to Voyager 2. Voyager 1 sped through tendrils of interstellar particles that had pierced the heliopause like tree roots through rock before passing through it. However, Voyager 2 observed a thin stream of low-energy particles that continued more than 100 million miles past the heliopause. As Voyager 1 approached the heliopause by 800 million miles, a new mystery emerged as it entered a region resembling limbo where the outward solar wind slowed to a crawl. Voyager 2 observed the solar wind forming a completely different type of layer before it crossed the heliopause, which strangely was almost the same width as the static layer seen by Voyager 1. More specifically, prior to the Voyager missions, astronomers projected that as one traveled further and further away from the Sun, the solar bubble simply disintegrated into interstellar space. There is a fairly clear barrier there, Voyager 2 appears to confirm. Plasma densities that Voyager 2's plasma wave instrument ultimately measured were very similar to those that Voyager 1 picked up. The density of plasma increases by a factor of 20 to 50 as you cross the boundary between solar plasma, which is extremely hot, approximately 1 million degrees Celsius, and interstellar plasma, which is exceedingly cold, only 10,000 degrees Celsius. That is a property of fluids, which frequently produce boundaries that are extremely sharp. The fact that both Voyagers passed the heliopause at the same relative distances, 121 astronomical units and astronomical units AU respectively, startled scientists the most. Previous models made strong predictions that the bubble's boundary should have moved farther out due to increased solar activity during Voyager 1's flyby in 2012. The heliopause should have retreated a little bit during Voyager 2's passing last year during a period of low solar activity. There is now some misunderstanding about the fact that both spacecraft left the solar system at two quite different locations, yet at roughly the same distance. Additionally, Voyager 2 made several discoveries that, at least in our opinion, don't line up with a sharp border. The magnetic field measurements both inside and outside the bubble are the largest of these. The magnetic field's orientation between the two was predicted by astronomers to be substantially different. However, as Voyager 1 and 2 both noted, there was essentially no change in the field's direction as they crossed this thin surface. At the same time, Voyager 2's magnetic field observations imply that it encountered a simpler, thinner heliopause than Voyager 1 did, one that was filled with less energetic particles. Once more, the sum of all this information begs more questions than it can answer. The rest of the solar system is shaped by coronal mass ejections, CMEs, which the Sun frequently spews forth as shock waves of plasma. It appears that the Sun's influence extends beyond its own area. The data from Voyager 2 and Voyager 1 before it demonstrates how coronal mass ejections spread past the heliopause and reduce the cosmic ray flux beyond the bubble. This resembles what you may learn about the galaxy in some ways. Although far more intensely than coronal mass ejections, supernovae agitate the interstellar medium by sending shock waves out into the galaxy as well. Most scientists agree that a supernova's interstellar shock wave caused even the solar system to form. These results support the hypothesis that the Sun may also affect the evolution of life on other worlds, both in our solar system and elsewhere, if we consider the possibility that cosmic rays may cause biological mutations in life on Earth. We will continue to learn from the two missions about how the Sun's heliosphere interacts with interstellar space, and they will also provide us with information about other star systems. We only managed to cross this entire bubble with 2 points. 2 instances are insufficient. A more comprehensive understanding of the heliosphere is necessary to solve these mysteries. Both Voyager 1 and Voyager 2 left the heliosphere close to its leading edge when it collided with the interstellar medium. The shape of the heliosphere's wake is unknown to us because we lack data on it. The heliosphere may be roughly spherical due to the pressure of the interstellar medium, but it is also plausible that it has a comet-like tail or is shaped like a croissant. However, as other spacecraft are now traveling outside our solar system, they won't be able to collect data from the heliopause. At more than 31,000 miles per hour, NASA's New Horizons spacecraft is leaving the solar system. When its power runs out in the 2030s, it will stop moving more than 1 billion miles shy of the heliosphere's outer border. For this reason, Voyager researchers and others are advocating for a further interstellar mission. A 50-year mission with multiple generations is intended to study the solar system's furthest regions before moving on to uncharted territory beyond the solar wind. However, the heliopause observations nearly served as the final act for both spacecraft. Solar power isn't practical in the enormous void of outer space, which is unfathomably far from our Sun. Because of this, engineers installed 3 radioisotope thermoelectric generators, or RTGs, on each Voyager. These function by generating energy from the heat produced by the radioactive fuel, plutonium-238. They essentially function as nuclear batteries, and they are eventually losing power at a predictable rate of 4 watts annually. The Voyagers don't require much power for propulsion, but it is necessary for them to be able to gather scientific data on distant magnetic fields and charged particles, which is now the sole option for humanity to do so in interstellar space. NASA started looking for ways to extend the instrument life of the Voyagers a few years ago. In 2019, the first step was to begin shutting off the heaters for the scientific apparatus. That was successful. The equipment continued to function despite a 50 degrees Celsius reduction in temperature, which was far colder than the settings in which it had been tested. However, it was still insufficient. So at the end of March, a NASA team implemented an energy-saving method on Voyager 2 that draws on some reserve power intended to safeguard systems from voltage spikes. Despite the fact that this tactic makes the vessel more vulnerable, Suzanne Dodd, the project manager for Voyager at NASA's Jet Propulsion Laboratory in Southern California, claims that the likelihood of such increases appears to be quite low. If everything goes according to plan, Voyager 1 might begin using a comparable power management system soon. Dodd believes that taken combined, this could extend the scientific mission of the probes by a few years. According to her, Voyager is still on a mission of discovery, and every bit of information the spacecraft gathers in interstellar space is important. Voyager 1 is currently 159 astronomical units from Earth, and Voyager 2, which is currently moving in an opposite direction, is 133 astronomical units away. The spacecraft are undoubtedly displaying symptoms of aging. The team had to cope with telemetry issues on Voyager 1 last year, but the cosmic workhorses are still going strong. It's not unusual for NASA missions to last far longer than anticipated and to receive extensions after finishing their primary tasks. Instead of 3 months, the Opportunity Mars rover continued to move for nearly 15 years. Instead of 4 years, NASA and the European Space Agency maintained the Saturn-focused Cassini mission for 20 years. But the Voyagers unquestionably win the cosmic prize. The two could reach the unheard-of age of 50 if Dodd's team's energy-saving strategy succeeds, with a stretch goal of reaching 200 astronomical units around the year 2035. However, doing so will necessitate sacrificing each science tool individually. A magnetometer, a plasma wave surveyor, a plasma science experiment, a cosmic ray detector, and a low-energy charged particle detector are the 5 experiments that remain operational on Voyager 2. The first 2 will probably be the last to be turned off because they only consume approximately 2 watts to operate and have electronics built right into the probe. The others consume between 3 and 5 watts apiece and are located on the vessel's boom where it is extremely cold. By turning each of them off, the craft would gain an additional year of life. Although it may appear that interstellar space is absolutely empty, there are still solar particles and magnetic phenomena to investigate. We truly have no idea what we might find, so the farther away from the sun we go, the more exciting it gets. And having 2 Voyager spacecraft is similar to using binoculars to view an object. For instance, astronomers predicted that the sun's magnetic field would progressively rotate in the direction of the interstellar medium outside of the heliosphere, and that the Voyagers would be able to observe that. However, they haven't yet observed this rotation, indicating that the magnetic field models need to be updated. Additionally, the spacecraft used its instruments to study interstellar matter and to find radiation from a dazzlingly intense gamma-ray burst that occurred in another galaxy in October. The continuous solar science conducted by Voyager will be utilized by missions based on more recent probes. NASA intends to launch the Interstellar Mapping and Acceleration Probe, IMAP, in 2025 in order to map the heliosphere. The measurements from the far-off probes may be compared to those from the much closer new one because the Voyagers are already well outside of the heliosphere. It will be lovely to have the Voyagers there for the Interstellar Mapping and Acceleration Probe. The Voyagers will also be taking useful measurements close to Earth, as we are witnessing with Interstellar Mapping and Acceleration Probe imaging, according to Princeton physicist David McComas, who is also the Interstellar Mapping and Acceleration Probe collaboration's leader. He compares it to medical professionals performing a brain biopsy in addition to a CAT scan to get a comprehensive picture of the patient's condition. Even though the Voyagers haven't finished, their legacy is already incredibly strong. Included in this is NASA's New Horizons spacecraft, which passed Pluto in 2015. That spacecraft, which is currently 55 astronomical units from Earth, is exploring the heliosphere's edge with sensors that are better and newer than those used by the Voyager spacecraft. It has already captured images of objects like Pluto's moons and the Arrokoth object in the Kuiper Belt that were unknown at the time of the Voyager's launch. Engineers are already developing concepts for next-generation spacecraft, such as ones that could be driven by lasers and light sails that could one day whiz into our interstellar surroundings quicker and farther than 1970s probes could. This is inspired by the Voyager's phenomenal performance. Voyager 1 and 2 are likely to continue their record-breaking missions for years to come as long as both are healthy, but someday they'll be living dead. Naturally, NASA was aware that this day would arrive before the missions even took off. Some scientists couldn't pass up this lone one-way ticket out of the solar system. Carl Sagan was so intrigued by the concept that he assisted NASA in developing a complete cultural component for the mission out of fear that one of the Voyager probes may be discovered by future extraterrestrials or space-dwelling humans. A team headed by Sagan selected the contents of each spacecraft's golden record, which serves as a time capsule from Earth. These messages to the sky include images and sounds from Earth, music from dozens of nations, and greetings in 55 different languages. Therefore, even though the Voyager probes will eventually stop communicating with us, this may not be the final communication they send as they travel across space. Our sun, then a swollen red giant star, will have scorched Earth to a cinder in billions of years. However, the Voyager record will still be mostly intact in some other isolated area of the Milky Way galaxy, retaining a faint memory of a long-gone civilization that once prospered on the faraway planet Earth, possibly before moving on to greater feats and other worlds. Thanks for watching another episode of Voyager. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.